My name is Jeff Berman. I'm a professor at University of Washington. Thank you, Maria, for the very nice introduction. And what we have today is kind of a topic that I extracted directly from kind of my advanced earthquake engineering course that I teach. That's kind of the end of our master's in structural engineering at the University of Washington. This is essentially the pieces, the conceptual building blocks that we need as structural engineers to understand probabilistic seismic hazard analysis enough that we can communicate with our geotechnical engineering colleagues on projects where you have to do site-specific seismic hazard analysis. And so that's our goal, is the kind of learning objectives, if you will, are not to necessarily become experts in probabilistic seismic hazard analysis. There are a lot of other folks that do that work, but instead, as structural engineers, to understand the key underlying assumptions and uncertainties that are considered in the process, and be able to kind of use the results in a educated way to do our structural design of buildings. Okay, so with that, we'll take it off. We'll take off. I have kind of a basic background of seismology concepts, and many of them you've seen before, and we'll just go quickly through them. And then we'll talk about what it is, what are the parameters that we're trying to predict in probabilistic seismic hazard analysis. Then we will turn our attention to first the deterministic version of seismic hazard analysis, where uncertainties are not considered, just to develop our kind of key understanding of some of the key principles. And then we will add uncertainty to all of those different areas and show you the framework for probabilistic seismic hazard analysis. And then we have a few kind of other topics at the end that come up quite a bit when you're designing buildings in high seismic zones, doing site-specific seismic hazard analysis, and corresponding nonlinear analysis of the buildings. And so we'll talk about those few things as well. Kind of as additional topics. Okay, so some credits before I kind of begin. Some of the slides and graphics are from course notes that I use at the University of Washington. Some of those are from notes that originally were developed by Steve Kramer, and I've kind of taken them and adopted them and for my own course and used them in different ways. So credit to my emeritus geotechnical engineering faculty colleague, Steve Kramer. And then also some of the slides and graphics are extracted from Geotechnical Earthquake Engineering, first edition, although there is a second edition that is out, and that is Steve Kramer's book on the topic. And then also I adopted some slides and some graphics from Elements of Earthquake Engineering and Structural Dynamics, third edition, which is a 2013 book by André Filiatreau and Robert Tremblay and Konstantin Christopoulos and others. So that's kind of the background and where some of this information comes from as I, use this stuff in my course. Okay, so first a review of seismology concepts. I'm not going to spend a lot of time on kind of high school level earth mechanics, but as you all know, we reside on the crust of the earth, which is made up of these plates that kind of move around. A lot of that movement is generated by the thermodynamic processes going on in the mantle of the earth, and the crustal plates kind of ride around, if you want to think of it that way, on the thermodynamic pushed flow of the mantle itself. And if we kind of look at the plate boundaries, what we see is places where we could have earthquakes. These are faults, essentially the boundaries between plates. There are spreading ridge boundaries, which are not actually faults, but areas where the two plates are moving apart from each other. We have convergent plate boundaries, where the plates are kind of pushing towards each other. And then we have transform plate boundaries, where they are moving kind of parallel to each other, but say in opposing directions. And then some of the interesting things is that when plates run into each other, one of them actually kind of takes a nosedive into the mantle. And as it's doing that, it's kind of compressing whatever other plate it's kind of pushing against, creating what we call a subduction zone boundary. And those subduction zone boundaries are where we can generate kind of the largest earthquakes on Earth, but also kind of in the region of those subduction zones, the upper crust kind of fractures into a whole bunch of small crustal faults. It can be an entire network of crustal faults that occur in those areas.